Welcome to our latest video on the topic of electron arrangements of D block and transition metal elements. This video is suitable for A-level students. By the end of this video lesson, you should be able to recall how to write electron arrangements for S and P block elements. You should also be able to understand and explain the meaning of the terms transition metal and D block element. And finally, you should be able to explain how electrons are arranged in transition metal atoms and ions and be able to write their electron configurations. Now in year 12 we taught you that electrons are arranged in energy levels, and within these energy levels we have orbitals. So let's recap how we would write the electron configuration or electron arrangement for magnesium. So magnesium is atomic number 12, so it's got 12 electrons, so it would be 1s2, 2s2, 2p6, and then I've added 10 electrons, so there's 2 left, so it would be 3s2. Now magnesium is classed as an S block element because when filling the orbitals, the last electron that we fill goes into an S orbital, so it's an S block element. So I'm now going to place the electrons into the boxes that represent orbitals, so they fill singly before pairing occurs. So it's 1s2, 2s2. I'm now putting the electrons in the 2p orbitals and they fill singly before pairing. So it's 2p6, and then the last electrons go into the 3s orbital, and again they go in singly before pairing, and magnesium's classed as an S block element because the last electron that I place into an orbital is in an S orbital. So now let's look at a second example. So phosphorus is atomic number 15, so it's got 15 protons and 15 electrons. So now let's write the electron arrangement or electron configuration for phosphorus. So it would be 1s2, 2s2, 2p6, because there's 6 electrons can go into the p orbital, 3s2, and then I've added a total of 12 electrons, so we've got 3 left, so it would be 3p3. Now phosphorus is classed as a p block element because when filling the orbitals, the last electron is going into a p orbital, so therefore it's classed as a p block element. So now I'm going to put in the electrons in the boxes to represent orbitals. So again, I represent an electron with a single-headed arrow, so I'm filling them singly before pairing occurs. So you can see it's 1s2, 2s2, 2p6. Again, I put them in singly before I pair them up. So the last electron is going into a p orbital, so therefore phosphorus is classed as a p block element. So is our next example calcium. Calcium's atomic number 20, so it's got 20 protons and 20 electrons. So its electron arrangement would be 1s2, 2s2, 2p6, 3s2, 3p6, and this time the 4s fills before the 3d because it's slightly lower in energy, and you can see on the left hand side about this. So therefore it would end in 4s2, and calcium is an S block element. So now let's put the electrons in the orbitals so they fill singly before pairing. So it'd be 1s2, 2s2. Then I put the 2p electrons in singly and pair them up. Then I put in the 3s electrons. I put them in singly before pairing. Then I put in the 3p electrons singly and pair them up. Now instead of putting electrons next in the 3d orbital, the 4s orbital fills before the 3d because it's slightly lower in energy, and therefore the electron arrangement ends in 4s2, and therefore it's classed as an S block element. Now it's important to mention that when writing electron arrangements for the elements after calcium in the periodic table, you would fill up the 3d orbitals, and the 3d orbitals can hold up to 10 electrons. So you would fill those in, and then you would start to fill in the 4p orbitals after that. So now let's test your understanding of writing electron arrangements or configurations with some practice questions. You will need a periodic table for this because you will need to find the atomic number for these elements. So read through the questions, pause the video, have a go at them, and then we'll go for the answers. So for the first question, you're asked to use the convention of representing electrons by arrows in boxes to give the electronic configuration of an atom of sulfur. So if you use your periodic table, you can see that sulfur has an atomic number of 16. So this means it's got 16 protons and 16 electrons. So I put in these 16 electrons using single-headed arrows, and I fill each orbital singly before I pair them up. So it will be 1s2, 2s2, 2p6, 3s2, and then I have 4 electrons left. So I put them in singly, and then I pair up the last electron. Now sulfur is classed as a p block element because its last electron is being put into a p orbital. Now for question 2, we have to do the same thing for aluminium. Aluminium is atomic number 13. So once again, I put them in singly, and then I pair the electrons up. So it'll be 1s2, 2s2, 2p6. So I'm just pairing the 2p electrons up here. Now there's 3 electrons left, so they go into the 3s and 3p orbitals. So it's 3s2, 3p1, and aluminium is therefore classed as a p block element. So now have a go at question 3. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So for question 3, you're asked to write the electron arrangements for the following elements and name the block in the periodic table that each is located. So potassium is atomic number 19, so its electron arrangement will be 1s2, 2s2, 2p6, 3s2, 3p6, and then you have to remember that the 4s fills before the 3d, and 1 electron goes into the 4s orbital, so it ends in 4s1. And because the last electron is being filled into an s orbital, it's an s block element. Now germanium is atomic number 32, so it's 1s2, 2s2, 2p6, 3s2, 3p6, and then once again the 4s fills first, so it's 4s2, then it's 3d10, and there are 2 electrons left because I put in 30, so it ends in 4p2. And germanium is a p block element because its last electron is in a p orbital. So bromine is atomic number 35, so it's 1s2, 2s2, 2p6, 3s2, 3p6. Now the 4s fills before the 3d because it's slightly low in energy, so it becomes 4s2. Then I fill the 3d orbitals, so it's 3d10. There's 5 electrons left, so they go into p orbitals, so it ends in 4p5. Now because the last electron is going into a p orbital, it's a p block element, so there's 1 mark here for each correct electron configuration and 1 mark for the correct block. So this slide summarizes the blocks that we've come across in the periodic table. So elements in groups 1 and 2 are classed as s block elements because when you fill their orbitals, the last electron is going into an s orbital. And elements in groups 3, 4, 5, 6, 7 and 8 are classed as p block elements. Now between groups 2 and 3 in the periodic table we have d block elements, and in this video and upcoming videos we're going to look in detail at these elements. And I've also included on this slide f block elements which we don't cover at A level, but I've included them just so you are able to understand where they're located in the periodic table. So now we're going to look at the electron arrangements or configurations of d block elements. Now the d block elements are the elements between groups 2 and 3 in the periodic table, and we're going to look at scandium to zinc. Now AR stands for the electronic arrangement of argon, which is 1s2, 2s2, 2p6, 3s2, 3p6. So scandium has 3 more electrons than I need to put into orbitals. So the 4s fills first and then the 3d. Now titanium is 4s2, 3d2, so I'm going to put these in. Vanadium is 4s2, 3d3, so again we put the electrons in singly before pairing them up. Now chromium has an irregular electron arrangement. It is not 4s2 3d4, it's 4s1 3d5. And this is because there's extra stability associated with having a half-filled D shell. So that's why the irregular electron arrangement takes place. So manganese is 4s2 3d5. Iron is 4s2 3d6, so I'm going to put them in singly and then I'm going to start to pair them up. Cobalt is 4s2 3d7, so again I put the electrons in singly using single-headed arrows and then I pair them up. And nickel is 4s2 3d8, so again I put them in singly and then I pair them up. Now you would expect copper to be 4s2 3d9, but it's not. It's 4s1 3d10. It's another element that has an irregular electron arrangement, so it doesn't follow the pattern. And this is because there's extra stability associated with having a full D shell, just like there is with a half-filled D shell. And the last one is zinc, and that is 4s2 3d10. So again, I put them in singly, and then I pair the electrons up. So when writing the electronic configurations of the D block elements, you have to remember these two irregular electron arrangements. So chromium is 4s1 3d5 because there's extra stability associated with having a half-filled D shell. So therefore, it uses one of its 4s electrons to achieve this. And copper is 4s1 3d10 because there's extra stability associated with having a full D shell. So copper uses one of its s electrons to achieve this. So we're now going to look at the difference in the terms D block elements and transition metals. Now, not all D block elements are classed as transition metals, and the definition of a transition metal can vary between A-level syllabuses, so it does depend which exam board you are studying for. Now, transition metals are usually thought of as elements that have at least one or more stable ions with a partially filled D shell. Now, we've already come across the fact that when writing electron configurations of D block elements, the 4s orbital is filled before the 3d orbital, and that's because in an empty atom the 4s orbital has a lower energy than the 3d orbitals. However, once the electrons are in their orbitals, the energy order changes. Now, this is because the energy order depends on the attractive and repulsive forces that exist between the electrons and the rest of the atom. So, for example, the nucleus, which has a positive charge. Now, once the electrons are in their orbitals, the 4s orbitals for the mainstay behave as the outermost higher energy orbitals. And therefore, when transition elements lose electrons to form positive ions, it is the 4s electrons that are lost first, and followed by the 3d electrons. So the diagram on the right hand side here shows that once there's electrons in the orbitals, the 4s is the higher energy orbital. That is not the case when we're dealing with an empty atom. So you have to remember that the 4s fills before the 3d because it is lower in energy for an empty atom. However, once there's electrons in these orbitals, the 4s becomes the outer orbital, and the 4s electrons are lost first. So to summarize, the 4s orbitals fill first because they're lower in energy than the 3d, and electrons in the 4s orbitals are removed first because once there's electrons in the orbitals, they become the outermost electron orbital. So now let's look at this in practice by writing the electron arrangement for some transition metal ions. So if we start with the electron configuration for Fe3+, Now, an Fe3 plus ion means that the iron atom has lost 3 electrons. So to do this, we first have to write down the electron arrangement for iron. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now when we remove 3 electrons from the iron atom, we have to remove the 4 s electrons first, because remember I've said that when electrons are in orbitals, the 4s orbital is the outer highermost energy orbital here. So we remove 2 electrons from the 4s orbital. Then we have 1 more electron to remove. So we remove this from the 3d orbitals, and therefore iron 3 plus has an electron arrangement 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. So iron is classed as a transition metal as it contains at least 1 stable ion with a partially filled D shell. Now iron 3 plus is the more stable form of iron, and you can see clearly it has a partially filled D shell. Now by a partially filled D shell, we mean it can't be empty and it can't be full, and it must have between 1 and 9 electrons present in it. So if it's got either 1, 2, 3, 4, 5, 6, 7, 8 or 9 electrons in its D shell, it is classed as a partially filled D shell. Now you can see it's got 5 here, so it's classed as a partially filled D shell. So iron 3 plus is an iron with a partially filled D shell. It's a stable ion. So the metal iron is classed as a transition metal. Now in this second example, we're asked to write the electron configuration for Cu2+. So to answer this question, we first have to work out the electron configuration for copper. So copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Now remember, copper is irregular in terms of its electron arrangement because it uses one of its 4s electrons to take the opportunity to have a full D shell, which has extra stability. Now, in this question, we're asked to work out the electron configuration for Cu2+. So Cu2+ means that we've lost 2 electrons. So to remove the 2 electrons, we take 1 from the 4s and 1 from the 3d orbital, and therefore it ends in 3d9. Now, copper is classed as a transition metal as it fulfills this definition of having at least 1 stable ion with a partially filled D shell, and this is because it's got 3d9, and therefore that is partially full, and therefore copper is classed as a transition metal. Now, as I've mentioned, the most common definition of transition metals is that they're elements that have at least 1 or more stable ions with a partially filled D shell. Now, zinc is therefore not classed as a transition metal as it only forms Zn2+ ions, and these ions don't have partially filled D shells. The Zn2+ ion has a full 3D shell, i.e. 3d10. So you can see here that zinc is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. If we remove 2 electrons, we remove them from the 4s orbital. So zinc 2+ ends in 3d10. So by this definition, zinc is not classed as a transition metal. Now, it shouldn't be a great surprise to you that zinc is not classed as a transition metal if you think back to GCSE, because at GCSE we learnt that transition metals are characterized by having coloured compounds and coloured solutions, and zinc compounds tend to be white and their solutions are colourless. Now, by this same definition, scandium would also not be classed as a transition metal, as scandium only forms Sc3+ ions. And an Sc3+ ion, where you lose 3 electrons, would mean that this ion would have an empty D shell, because scandium's electron arrangement is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. If you lose 3 electrons, it ends in 3p6, and you'd have an empty D shell. Now, we've discussed previously that the traditional definition of transition metals is that they're elements that have at least one or more stable ions with a partially filled D shell. Now, IUPAC, the governing body of chemistry, has extended this definition in recent years to include atoms that have partially filled D shells. Now, in this new definition, zinc is still not classed as a transition metal, but scandium is. Now, this is because the element scandium has atoms with partially filled D shells, even though its ions do not. So if we look at the electron configuration of scandium, you see it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2, and it does have an atom with a partially filled D shell. It's got one electron in the D shell. Now, its only stable ion is Sc3+. So this is 1s2, 2s2, 2p6, 3s2, 3p6. This has an empty D shell. So it's classed as a transition metal by this new definition because its atom has a partially filled D shell. By the old definition, it wouldn't be classed as a transition metal because its only stable ion has an empty D shell, not a partially filled one. Now, if you're studying the WJC course, this is the definition that the WJC use. So they would class scandium as a transition metal because they would use this extended definition. So now let's test your understanding of this with some practice questions. So here's our first question. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go for the answers to question 1. So you're asked to give the full electron configuration of the following. So manganese would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2. Now chromium's electron arrangement is irregular. It's 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Because remember, it uses one of its 4 s electrons to enable it to have a half-filled D shell, which is more stable. So for Mn2+, 2 electrons have been lost from manganese, and these 2 electrons would be lost from the 4s orbital. So the electron arrangement is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. And the last one is chromium 3+. So here we have to lose 3 electrons from chromium, so we lose 1 from the 4s and 2 from the 3d, so it would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. Now each correct electron configuration is worth 1 mark. So now have a go at our second practice question. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. Now for question 2, you're asked to use the convention of representing electrons with arrows in boxes to give the electronic configuration of iron and iron 3+. Now iron has an atomic number of 26. Now argon is 18 in terms of its atomic number. So you have 8 electrons to put into the boxes. So we fill the 4s first. So it's 4s2, and then there's 6 electrons to put in, so I'm putting them in singly before I pair them, so it would be 4s2, 3d6. And for iron 3+, I have to remove 3 electrons, so the electrons are removed from the 4s first, and then the 3d. So if I remove 2 electrons from the 4s, and then 1 from the 3d, I'll be left with the electronic configuration for iron 3+, which will be 3d5. So I'm putting these electrons in and I fill them singly before I pair them up. So there's 1 mark here for each correct electron arrangement. Now here's our last question for you to have a go at. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So question 3 is asking the following. It says atoms of copper and zinc both have full 3D shells. Explain why copper is classed as a transition metal but zinc is not. And this is a 2-mark question. Well, copper has a stable ion, Cu2+, with a partially filled D shell. If you said that, there's 1 mark. And you can see I've illustrated this here by putting the electron arrangements down for copper and copper 2+. And you can see clearly that copper 2+ has a partially filled D shell, 3D9. Now, zinc does not have atoms or ions with a partially filled D shell. And if you said that, there's 1 mark. And you can see I've illustrated this by putting the electron arrangements of zinc and zinc 2+ down on this slide. And you can see for both, the D shell is full. So that concludes this video lesson. So after watching this video, you should be able to recall how to write electron arrangements for S and P block elements. You should also be able to understand and explain the meaning of the terms transition metal and D block element. And finally, you should be able to explain how electrons are arranged in transition metal atoms and ions and be able to write their electron configurations. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.